13 here. Last time we finished up, I think, 7, which was about reactions and ways to classify reactions. So today we're going to talk about gases, and we're going to talk about gases and gas laws. When we talk about gases, obviously we're in the state of matter where everybody has broken apart from one another. They are flying around. There are collisions that occur. And as we'll talk about in this chapter, really the number of collisions that occur relates to pressure. And that's usually what we sort of associate with gases is the pressure there is with those gases. It is directly really related to the number of collisions that occur. As we'll talk about, the more collisions there are, the more pressure it is. The less the number of collisions, then obviously the less the pressure. So let's start with talking about sort of what substances, sort of exist as gas under normal conditions. So when we talk about normal conditions, that's usually sort of what is sometimes referred to in normal circles as sort of standard conditions, everyday conditions. And that's usually a temperature of 25 degrees Celsius and a pressure of 1 atmosphere or ATM. So ATM is a unit of pressure. If you ever look as you continue through chemistry and you have to look up values, for example, in tables, those are usually the two conditions that those tables were made from. The pressure is usually 1 atmosphere and the temperature is usually about 25 degrees Celsius. And that's sort of considered normal temperature, normal room temperature, normal sort of conditions. Now, under these sort of normal conditions, if we're doing something that's ionic, which obviously, as we know, hopefully by now, is a metal and a non-metal together, they typically do not exist as a gas under normal conditions. And that's because of the really strong attractive force. And I think we've touched upon it as we've gone through some of these chapters. Probably one of the strongest sort of attractive forces you could have is that electrostatic attraction between the positively charged cation and the negatively charged anion that holds that together. So under normal conditions, we really do not tend to see ionic compounds in the gas phase because pretty much it's too strong of a force to get them apart. So that attractive force between those ions is really, really a strong force. What typically happens with ionic compounds, and maybe you experienced some of this earlier on in the semester when you did some of those labs, typically what will happen if you continue to heat an ionic compound in something like an evaporating dish, for example, it will really just start to melt before it will actually go into the gas phase. So we know that, for example, if you put like sodium chloride or salt on things and you heat it up, it doesn't become like sodium metal and chlorine gas, right? It'll actually still be there in that sort of form. So ionic compounds typically are not found as gases under normal conditions. When we talk about molecular compounds, and remember the main difference between those two, ionic and molecular, is ionic compounds, there's absolutely no sharing of electrons, so we create those ions which are attracted to each other. In molecular compounds, those are pretty much nonmetals and nonmetals together, so that's nothing but sharing of electrons. And as we talked about in the bonding chapter, that sharing may be equal, it may be unequal, but there's some aspect of sharing that occurs. So we do see a lot of difference between molecular compounds and ionic compounds in terms of phases. There are some molecular compounds like carbon monoxide, carbon dioxide, that's hydrogen chloride gas, ammonia, and methane, which is CH4. These are gases under normal conditions. But a lot of molecular compounds are liquids and solids under normal room temperature. But one of the sort of major differences between an ionic compound and one of these molecular compounds is it is usually much easier to convert a molecular compound into the gas phase than you can an ionic compound. And it's really because of how those molecules are held together. So for example, if we take something like water, which is a polar molecule, and water, which is a polar molecule, has more negative on the oxygen, more positive charge on the hydrogens. When you have two water molecules together, for example, they are held together by what is referred to as an intermolecular force. and it's the positive side of one to the negative side of another. That is what is known as an intermolecular force. And an intermolecular force is the force that holds basically one whole molecule together with another. And all intermolecular forces are actually just positive negative attractions, is essentially what happens. The positive side of one molecule is attracted to the negative side of another. So this particular intermolecular force is what is known as hydrogen bonding. We'll talk about in chapter 14 officially. But hydrogen bonding is that force that holds one entire water molecule together with another water molecule. Now, if you were to look at just one individual water molecule, there are individual covalent bonds here, right? The electrons being shared between the oxygen and the hydrogen, and the oxygen and the other hydrogen as well. So these covalent bonds are what are referred to as intramolecular forces. Intramolecular forces means within the molecule itself, like covalent bonding. Now, intramolecular forces are always much stronger than intermolecular forces. And water is an example of that. For example, when we heat up water, we know that when we get to 100 degrees Celsius, that bond between that water molecule above and below will break. And that's going to allow each of these individual water molecules to go off into the gas phase, basically to create steam, right? So that basically go off into the gas phase and create some steam. And we know that's what happens because if we heat up water, we know we do not break the intramolecular force, because if we broke the intramolecular force, we would actually break the bonds between the oxygen and the hydrogen in each of the individual water molecules. That would generate a lot of hydrogen gas and oxygen gas, which would not be great. For example, if you were trying to cook some pasta, right, boiling water, you start creating hydrogen gas, oxygen gas, you probably don't get to the pasta part of the dinner. So that doesn't happen. So intermolecular forces, the forces that hold one particular molecule together with another, is always weaker than the intramolecular force. The forces, they're basically like sharing electrons in a lot of cases, that hold an actual individual molecule together. Now, why do some, for example, easier to get to the gas phase? Why are some just in the gas phase to begin with? Let's take something like methane here. If we take something like methane and we draw methane, like a little Lewis structure type action, right? Methane is a nonpolar molecule. And we know that the bond between carbon and hydrogen is nonpolar. The entire molecule is symmetrical as well, so it's nonpolar. And what happens when you put something like methane together with another methane, what holds these two guys together is also an intermolecular force. This is actually what is known as dispersion forces, which we'll talk about in chapter 14. Dispersion forces are actually the weakest intermolecular force you could have. You basically could just look at it and it's going to want to basically break apart. They're typically very temporary type of attractions. And that's why when you think of something like methane, which is the gas that comes out when you light your Bunsen burner, it comes out normally as a gas. And that's because it's held together by super weak forces that basically they're not going to hold themselves together very much. Hydrogen bonding is actually a relatively strong intermolecular force, but it's still breakable by just heating it up to 100 degrees Celsius, right? We're at boiling point of water, and you could break that bond and get it to go into the gas phase. Something like methane, you actually don't need to actually heat it up. A lot of organic molecules are like that, so you're probably familiar obviously with methane, propane, butane, right? Those guys are all normally gases under normal conditions because they're all nonpolar molecules. They're all held together by super weak forces, and it's super easy for them to go into the gas phase. That's also why if you get to, are you going to take organic? If you take organic chemistry, a lot of the solutions that you use are what are known as being volatile. And what that means is they could go into the gas phase really, really easily, even if they're in a liquid. And that's why they usually stick you in a fume hood, because if you're using something like that and a flame, that's not a good combination. So that it could go into the gas phase really, really easily and could cause some not so great damage. In addition, you don't really want to smell that, right? Because it goes into gas phase, you're going to inhale it really good. So when you go to organic, a lot of organic molecules, because they are nonpolar and very volatile like that, go into the gas phase super easily. They oftentimes will you do a lot of your work in the fume hood to prevent those type of things happening. So in general, if something is held together through an intermolecular force that's relatively strong, we would not expect it to be in the gas phase under normal conditions, and that's like our ionic compound. If it's held together by a weaker sort of intermolecular force, it's going to be much easier for it to be in the gas phase. And again, that's what we see with a lot of organic compounds and stuff like that. Any questions on that there? So what are some substances that exist as gases under normal conditions? A lot of those diatomic elements, there are molecules, diatomic molecules that are elements are things like hydrogen, nitrogen, oxygen, fluorine, and chlorine. Those are typically gases under normal conditions. Obviously, group 8 on the periodic table, which is our noble gases, those are also going to be gases under normal conditions. Those noble gases are what are referred to as being monoatomic, which means they come as ones. So unlike hydrogen, oxygen, nitrogen that come as twos, those guys in group 8 do come as like one helium, one neon. They're not attached to residue 2. Ozone, which is O3, is also a gas under normal conditions. Um, Also why we put sunblock on sometimes, and depending on where it is in the atmosphere. Could be good, it could be bad, actually. So if you look at the periodic table, again, our normal sort of guys here, we got our gas. Right here is our gas, and obviously here are gases. Now, this is a good point to talk about the difference between a gas and a vapor. A gas is a substance that under normal conditions would be found in the gas phase of itself. And a vapor, on the other hand, is something that under normal conditions is actually not found in the gas phase. So a vapor is something that normally is maybe a liquid or a solid that can be converted into a gas. Probably the easiest example is the one we were just talking about, which is water, right? Under normal conditions, water is a liquid, but again, all you have to do is basically heat up water to 100 degrees or so, the boiling point, and you will turn it into water vapor, is what we typically refer to it. We don't refer to it as water gas because it just sounds funny, but we call it water vapor, again, because water is normally found in the liquid phase, but can be converted into a gas. So something like obviously hydrogen gas, which is normally found in the gas phase, is referred to obviously as a gas. Now, one of the most measurable sort of properties of gases, as I mentioned before, is pressure. And it is really associated to, as I mentioned earlier, the number of collisions that occur. Again, the more collisions, the higher the pressure. The less collisions, the lower the pressure. Uh, Air, right, is actually 78% nitrogen, right? It's actually the major component of air, followed by oxygen, and then other gases, depending on what air you're breathing, I suppose, is what's floating around in there. The density of air decreases as you go increasing distance from Earth. That's why we pressurize planes, right, when we fly and all that kind of stuff. Now, how do we measure pressure? One of the ways that we measure pressure is through a barometer. And a barometer is an instrument that measures pressure. A classic barometer, which we no longer have in labs, usually at schools, because it had mercury in it. They've taken most of them out. But a classic barometer is actually a pool of mercury. And in that pool of mercury is kind of like a glass tube, if you will. And basically what happens is in a traditional barometer, as the atmospheric pressure pushes down on the mercury rises in the tube. Mercury is actually one of those weird elements that actually has an inverse meniscus. It actually goes upwards instead of down. And you would actually read, in this case, the top of the meniscus is actually where you'd read for something like mercury, which is an unusual sort of property. Now, some of the units, which obviously you should be familiar with, 1 atmosphere. Again, an ATM is a no money, but a unit of pressure. We also have two other very common units of pressure that we see a lot, which is a torr and an mmHg. mmHg is millimeters of mercury. And millimeters of mercury because when you look at this glass tube, there actually would be like a ruler on the side of it. And you could read it usually in inches per mercury, or sometimes centimeters per mercury or millimeters per mercury. So millimeters is like you're reading off a ruler, and mercury because used to be obviously the liquid was a mercury in the barometer as well. The relationship between an ATM, millimeters of mercury, and a torr, which obviously was named after the guy who invented the barometer, is 1 ATM is 760 millimeters of mercury and 760 torr. A torr and a millimeter of mercury is a 1-to-1 relationship. So you do need to know these guys obviously here. So if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760. That will cancel out the atmospheres, get you millimeters of mercury or torr. If you're starting with torr, you're going to divide by the 760. Or if you're starting with millimeters of mercury as well, is an atmosphere. And that's going to cancel and leave you with atmospheres here. So that conversion is really good. There are definitely other units of pressure that you sometimes come across. But I would say if you want to think about kind of the big three in terms of units for chemistry, pressure, these are probably the big three there: atmospheres, torr, and millimeters of mercury. There are other units like pascals, kilopascals, a bar as well. A bar and an atmosphere are pretty close to each other. It's like 1.01 to 1. So they're fairly close in terms of value. Here's a picture of a barometer. And again, as I mentioned, atmospheric pressure comes down, mercury giving you kind of that upside down meniscus. And like I said, there usually is like a ruler type on there that you just take, actually just a ruler reading. And again, a lot of times it's in inches or centimeters, and we convert it to millimeters of mercury, which is a common one. So as I mentioned before, a few other sort of units. You probably should kind of know these guys as well. I will say you probably won't come across too much of these guys. At least in this class you won't, but down the road you might. But definitely those three from the last one we'll see probably more than these. But an atmosphere is equal to 101,325 pascals, or 101.3 kilopascals. And 14.7 psi, that's pounds per square inch. Like if you're blowing up your tire or a basketball or something like that, equals 1 atmosphere. And like I said before, this is one people don't use all that much, too much anymore, but a bar and an atmosphere, a bar is a unit. 1.01 bar is equal to 1 atmosphere. If you find some old books, a lot of times instead of atmospheres, they'll use bar as the unit of pressure. And again, it's fairly close, almost a 1-to-1 relationship with an atmosphere. So we're going to talk about gas laws now. And when we talk about gas law, there's three sort of variables that we deal with. We deal with P, which is pressure. We deal with V, which is volume. And we deal with T, which is temperature. Now, in some of these gas laws, we may keep one constant and maybe vary the others. We may actually vary all of them. But that is the three major sort of variables that we come across in gases. So let's talk about our first relationship here, and that is Boyle's law. And Boyle dealt with the relationship between pressure and volume, and he kept constant temperature. So Boyle dealt with that relationship of pressure and volume, keeping the temperature constant. And what he found was that if you keep the pressure constant, the gas is inversely proportional, the volume of the gas inversely proportional to the gas pressure. So what did he see? He saw this essentially as the volume goes up, the pressure goes down. So if you think about it logically in the sense of volume, right? If you have a really big volume, that will give all your gas molecules a lot more room to fly around in. And because it has a lot more room to fly around in, the number of collisions are going to be less, and that's going to result in a much lower pressure basically happening. Now, the other thing that he saw was if you decrease the volume, you will actually see an increase in the pressure. And if you just think about it graphically here or logically, if this is now my volume and I got my gas molecules in there, they definitely do not have a lot of room to fly around in. And there's going to be a lot of collisions that's going to occur in that smaller volume. The result of that is we're going to see the pressure go up as a result of the number of collisions. So the smaller the volume, usually more collisions, higher pressure. Larger the volume, less collisions, lower the pressure. So the relationship of Boyle's law is basically as one goes up, the other goes down. Now, another interesting thing about Boyle's law is if you did an experiment with Boyle's law and you took a bunch of pressure and volume measurements and kept the temperature constant, they will always equal, if you multiply those values together, the same number. It will always equal a constant number. This is what is sometimes referred to as a proportionality constant. So you could do this experiment under constant temperature, take a bunch of different pressure volume relationships. If you multiply those numbers together, you will always hit the same number. And that is what is known as a proportionality constant. Because of that relationship, what that allows you to do is actually set Boyle's law up under two different conditions. You can kind of have this is what we kind of think of as Boyle's law right there in our parentheses, our box. And obviously you do need to know these guys. P1 times V1 equals P2 times V2. Once again, this is at constant temperature. And as we talked about on the previous slide there, pressure goes up, volume goes down, pressure goes down, volume goes up. Now, what about the units? P1, V1 equals P2, V2. These are kind of like before and after conditions. So something changes, either the pressure changes or the volume changes as you go from left to right in this particular case. Now, in terms of the units, it really doesn't matter what the units are in this formula. The pressure can be any unit you want as long as they're the exact same on both sides of the equal sign. The volume, same deal. The volume can be any volume unit you want as long as they are the same on both sides. So you don't have to necessarily get them into a specific unit as long as both pressures are the same units and both volumes are basically the same unit as well. Any questions on that there? And this graph is a Boyle's law graph, and what we see here is at a much smaller volume, we have a much higher pressure. At a much larger volume, we have a much lower pressure. Again, bigger volume, more room for people to fly around in, less collisions basically occurring. So why don't you try one here? You take an inflated balloon, has a volume of 0.55 liters at sea level, which is 1 atmosphere, rises to 6.5 kilometers where the pressure is 0.4 atmospheres. Assuming that the temperature remains constant, you do that, it will point you in the direction of the correct sort of formula you should use. Although we've only learned one at this point, we're going to learn a bunch, obviously, as we go through this chapter. But that oftentimes will kind of point you in the right direction. So clearly here we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is actually useless information in this problem. We have another pressure here that is 0.4 atmospheres, and we are looking for a volume in this case as the temperature is held constant. So again, by just looking at this, you should hopefully point you in the Boyle's law direction here. As obviously we have two P's and two V's. Does it really matter which one you call 1 and 2? The answer really is no, it doesn't, as long as you keep the values that go together together. So usually people will just go in the order it's written in the problem. So I'll call these guys 1s, and I'll call these guys 2s in this case. The thing I do want to make sure of, which I'm okay in this particular case, is the unit of pressure on both sides are the same. If they were not the same, you do have to do a conversion. Again, it doesn't matter which one you convert it to, but you do need to make sure that they're the same. In terms of my volume, the units here are liters, and that's okay too. It just means when I get my answer, it's going to be in liters, so it doesn't really matter. So here using P1 V1 equals P2 V2, in this case, obviously, we are looking to solve for V2. Also, if rearranging formulas is not really your thing, then you could just remember kind of the easy rule here, especially with these type of formulas, which is whenever you move something to the other side of the equal sign, it ends up in the opposite location. So although these are not really written as fractions, you could think of them as a fraction. I need to move my P2 to the other side, so I could just take this guy basically and drop it there to the bottom, and I'll be in business there. P1, V1, P2 is equal to my V2 in this case. So again, things always move to the opposite side of the equal sign where they started. Remember as well, though, that if you are solving for something, whatever you're solving for does need to be on the top by itself. Yeah, so it can't be on the bottom. Otherwise, that's the inverse of it. So at this point, I want to make sure I put all my numbers in correctly. So my P1 is 1 atmosphere. My V1 is 0.55 liters divided by my P2, which is 0.4 atmospheres. Here again, our atmospheres are going to cancel. It is going to leave me liters, which is a unit of volume, which is good. So basically 0.55 divided by 0.4, that's going to give me 1.4 liters as my new volume in this particular case. First off, any questions on that there? Remember as well, it's a really good idea that if you understand, like we talked about a second ago, the relationship of Boyle's law, which is, again, as the pressure goes up, the volume goes down. As the pressure goes down, the volume goes up. You could sort of check your calculation to make sure that it kind of makes sense. In this case, when we look at the pressure, it went down, which means our volume actually should go up. And it started at 0.55 liters. It did go up to 1.4. So that's also something, a good thing to kind of take a look at, because sometimes it's very common people kind of reverse numbers and, put the guy on top that should go on the bottom and so forth. So that's a good way. If you ended up with a volume that's less than what you started with, you probably made some math mistake there along the way. Any questions on that? Yeah. It is 2 sig figs because all these numbers here are basically 2 sig figs, right? And basically all we did here in terms of math is multiply and divide, so everybody should end up at 2 in this case, yeah. Other questions? Okay. What was that one? So let's talk about the next sort of gas laws, and we're going to talk about two sort of gas laws here, Charles' law and Gay-Lussac's law. And in this case, they did look at a little bit different things, but kind of similar. Charles looked at the relationship between volume and temperature, keeping pressure constant. Gay-Lussac's law here looked at the relationship between pressure and temperature, keeping volume constant. So these two are the relationships that we see here. So let's talk about what happens first off in sort of Gay-Lussac's law here. Basically, his law was P1 over T1 is equal to P2 over T2. Once again, this is at constant volume. So what happens in this particular case? Well, when we think about the situation, let's say we have a gas molecules in this container is obviously at constant volume. And what happens is if I increase the temperature in this situation, my gas molecules are going to start to move around a lot faster, right? When you increase temperature, you give everybody a lot more energy. So what we would expect for our gas molecules in that increased temperature is they should start flying around a lot faster. Because they are flying around a lot faster, that should lead to more collisions. And the result of that is because it leads to more collisions, we actually should see the pressure start to increase in this particular case. So in Gay-Lussac situation, because there's a constant volume, if you increase the temperature, more collisions leading to a greater pressure. Now what happens in this situation if we lower the temperature? If we lower the temperature, our gas molecule is going to actually lose energy and it's going to fly around a lot slower, dramatically drawn here, much slower moving gas molecule. Because it is a slower moving gas molecule, that means it's actually going to have less collisions. And because it has less collisions, we would actually see the pressure start to decrease. So in the Gay-Lussac situation, because the volume doesn't move, the temperature plays a really big role in terms of the pressure. And as you increase the temperature, the pressure increases. As you decrease the temperature, the pressure decreases. First off, any questions on that there? Now, what about Charles' law? Well, if we look at Charles' law, his law is V1 over T1 is equal to V2 over T2. This is at constant pressure. So what happens in this situation is, let's take the example of I increase the temperature. If I increase the temperature like we saw over here on the right-hand side, and our volume was fixed, that is going to cause obviously a lot more collisions, and we would expect, like we see on the right, the pressure to start to increase. But we don't want the pressure to increase in this case. We wanted to keep it at constant pressure. So what happens in this situation of Charles' law is as we increase the temperature, the volume actually increases. So what happens is you get a lot more room for everybody to fly around in. And because they're flying around a lot faster because of the increase in temperature, by giving them the extra room to fly around in, what that ends up doing is keeping the number of collisions relatively constant. And that is what keeps the pressure constant. So in Charles' law, what happens is the volume adjusts to allow the pressure to remain constant. And vice versa, if I were to lower the temperature like I did over here, we would have much slower moving gas molecules, which would cause our pressure to decrease. So what happens in this case to keep the pressure constant is when you lower that temperature, the volume actually decreases. And once again, in that smaller volume, we're going to have the same number of collisions. So with Charles' law, the way it's able to maintain constant pressure is the volume actually adjusts, and the volume adjusts to allow the number of collisions to remain the same, and that's what keeps the pressure constant. Because in Gay-Lussac's situation, there is constant volume, there is no volume adjustment there. We get the pressure going up or down depending on what you do. Either you increase the temperature or lower the temperature. First off, any questions on those relationships there? Okay. Now, one of the interesting things, if you plotted a Charles law plot for any gas you choose, so we got like helium, methane, water vapor, hydrogen gas, and so forth. If you plotted volume versus temperature, and you did a straight line plot, and you extended those straight lines to the temperature line, every single gas, no matter which one you choose, they all hit the same spot. They all hit minus 273.15 degrees Celsius. That number should look familiar to you because that is the number you use to convert to Kelvin, right? So that is the number we convert to Kelvin. If we wanted to convert to Kelvin, you would add 273.15, giving you 0 Kelvin, which is known as absolute zero. So Kelvin recognized this sort of characteristic, and because of that, you could thank him because every single gas law ever that you use, the temperature always needs to be in Kelvin. So that should almost be an automatic thing that you do when you're doing a gas law problem. If you come across a temperature, you need to put it into Kelvin. So when we look back on our previous slide here, and you could have went forward, I suppose, these temperatures need to be in Kelvin. Yeah. And this temperature needs to be in Kelvin. And pretty much like I mentioned before, if it is a gas law, you got a temperature, you got to put it in Kelvin. Now, that's even on a question that tricks people a lot when they come across it. And the question is like this: they will give you the temperature in Celsius. They will ask you to find the temperature in Celsius. So people think, well, they gave it to me in Celsius. I got to find it in Celsius. I could leave it in Celsius, and you will get the wrong answer. So you do have to take it from Celsius, convert it to Kelvin, go into the gas law, and then convert it from Kelvin back to Celsius. So that's, again, a very common error that people make when they come across those questions where it's like, give you the number in Celsius, answer in Celsius, but you do have to convert it to Kelvin into the gas law and then convert it afterwards. Any questions on that there? So that again is our relationship that we talked about there. V1 over T1 equals V2 over T2. And again, Gay-Lussac's law, P1 T1 equals P2 T2. Constant volume, here constant pressure. Now, what about the pressure and the volume in these equations? Once again, it does not matter. You could have the volume in any unit you want as long as both volumes are the same unit. And the same thing with the pressure. You could have the pressure in any unit you want as long as both pressures are the same. So it is always the temperature that's super important here. All right, so once you try one here in an experiment, 452 milliliters of a gas using a light bulb goes from 22 to 187 degrees Celsius. What is the final volume? Eliminates that one, that eliminates that one, and it should kind of point you there to Charles' law. You should kind of, you can almost see it as you kind of label that. Once again, as long as we keep the numbers together, it doesn't really matter which ones we call 1 and 2. So I'm just going to go in order of the problem here, 1s and 2s. I do have a little bit of work before I could go into the formula. So once again, I see temperature. It should just be automatic on these guys. We need to add our 273.15 they want you to use here. The 273.15. Remember to use it. That's pretty good, I guess. 295.15 Kelvin and 460.15 Kelvin in this case. So if we take our Charles law here, V1 T1 equals V2 T2. Once again, we are looking for V2, which is this guy. As I mentioned, you could just do, again, kind of the quick way there. So we do need to get rid of T2, and we need to move it to the opposite location. So it was on the bottom. It should end up on top. We're really just multiplying it to both sides is basically what we're doing in this case. That will give us V1 T2 divided by T1 equals our V2. And again, here we're just going to put everybody in the correct spot. V1 is 452 milliliters. T2 is actually this guy, 460.15 divided by 295.15. Kelvins are going to cancel, going to leave us here milliliters, which is a volume, so that's good. So that's going to get us here 452 times 460.15 divided by 295.15. And we're going to end up with a 705 milliliters in this case. once again, if we understand our Charles law sort of application here, as the temperature increases, so does the volume. As the temperature decreases, so does the volume. Here, our temperature went up. That means our volume should go up. So it went from 452 to 705. So again, at least it went in the correct direction based on what should happen in this situation. Any questions on that there? All right. Yeah, it's saying six for the answer. Yeah, so what I would do is I'd take 452 and times it by, let me do it one more time here, just make sure, 460.15 and hit equals, and then divide it by 295.15 and hit equals. You should end up with 704.685. So you definitely want to multiply the top and then hit equals and divide it by the bottom, then hit equals. And you should hopefully get it, yeah. Ish. What was that? Okay. Yeah. Are you asking about the temperature? Uh, so you have to use the 273.15? Is that what you're asking? So I'll be honest with you. The answer is in every other place but here. You they want you to use the 0.15 here, so I would use the 0.15 going forward. Most places do 273, but at this particular school, they do want you to use 273.15. Okay. Did I misimpose the number? Oh, okay. Okay, so it's you got when at 425? Yeah, so make sure you did 452. There, okay. That's good because sometimes it's me. I do that sometimes. Like, oh, wait, I gotta get the number. Okay, so we're all good then. Yeah. Okay, perfect. Cool. All right. Let's talk about the next law, which is, of course, our good friend Avogadro, right? And when we think about Avogadro, we think about moles, right? Avogadro's number. And moles in gas laws is represented by the letter N. So when you see N in a gas law, that represents the moles. So it does sort of make sense that Avogadro's law involves moles. And Avogadro's law states that the volume of a gas is directly proportional to the moles of a gas. And this is Avogadro's law, which is V1 over N1 equals V2 over N2. Um, this is actually at two conditions. This is constant temperature and pressure. So under constant temperature and pressure, V1 over N1 equals V2 over N2. Now, Avogadro's law is like any other gas law. You can basically plug and chug into Avogadro's law and solve for something that's missing. Here, the volume doesn't really matter. It could be any unit you want as long as they're the same. Obviously, here the moles needs to be in moles. Also, a reminder that the very common way that we could get to moles is grams to moles, right? And again, the molar mass, right, from the periodic table is that conversion factor that we use to do that. So that's very common in gas laws that you have to convert grams to moles using the molar mass from the periodic table to do so. So Avogadro's law, you could use like any of the other gas laws, like I said, that you could just basically put into the equation and solve for it. Now, one of the sort of interesting things about Avogadro's law and Avogadro's relationship is, for example, here, as we can see, if we increase the volume to 2, we get 2 moles. If we increase it to 3, we get 3 moles. One of the relationships that comes out of Avogadro's law actually deals with stoichiometry. And we're going to talk about gas stoichiometry, which is basically the same idea as regular stoichiometry that we did in chapter 9. But with gas stoichiometry, usually at some point, what you have to do, as we'll talk about later on in this chapter, is you have to put it into a gas law usually. Now, if you happen to have a stoichiometry type problem here under constant temperature and pressure, and you're looking for like a volume of somebody, you could do stoichiometry here without a gas law. And if you remember, if we look at this equation, for example, we could say for every 1 mole of N2, we get 3 moles, right, of H2. For every 1 mole of N2, we get 2 moles of NH3. And every 3 moles of H2, we get 2 moles of NH3. So we could do our really mole-to-mole sort of stoichiometry relationship. But if you are at constant temperature and pressure, you could actually do a volume-to-volume relationship. So you could actually say, for every 1 liter of N2, I get 3 liters of H2. And again, instead of a mole-to-mole relationship, you could do a volume-to-volume relationship. You could also say for every 1 liter of N2, I get 2 liters of NH3. And again, I'm getting this relationship the exact same way I would do the mole-to-mole relationship, the coefficients from the balance equation. Instead of a mole-to-mole, it's a volume-to-volume. I could also do it for the last guy here as well. For every 3 liters of H2, I could get 2 liters of NH3. So if you find yourself in a stoichiometry problem that's at constant temperature and pressure and you got gases, and let's just say you want to know, for example, how many liters of NH3 would you produce if you started with 4 liters of H2? So you really could just do a stoichiometry problem, take the 4 liters of H2. You would do the liter to liter relationship in this case between H2 and the product. And for every 3 liters of H2, I get 2 liters of NH3. The liters of H2 would cancel. That's going to essentially give you 8 divided by 3. And that's going to give you, in this case, that you would produce 2.66 liters of NH3. So one of the things that this would allow you to do, as we will see a little bit more when we get to that part and later on this chapter, is you would not have to necessarily use a gas law to figure out an answer. You could still use a gas law, but you don't have to in this case because of Avogadro's relationship. But it does need to be under those conditions of temperature and pressure constant for you to do kind of a volume to volume relationship rather than a mole to mole relationship. Any questions on that there? All right, so obviously, as I mentioned as well, you could just use Avogadro's law like a normal gas law and just plug into there. So taking together all those gas law, or Avogadro's law, or Boyle's law, or Charles' law, and putting them together gives us the big gas law of the season here, which is PV equals nRT, which is known as an ideal gas law. And the ideal gas law, which is PV equals nRT, uh, is a little different than all the gas laws we've just seen. It is like a one and done situation. There is no 2 pressures, there's no 2 volumes, there's no 2 temperatures. It's just one of everything. Everybody else, you got 2 of everybody, right? So there is kind of like a no before and after. In addition, this is probably the most restrictive gas law that you could come across in terms of units. So when you use PV equals nRT, the pressure in this equation has to be in atmospheres. The volume in this equation has to be in liters. The moles should be in moles. And obviously, like any other gas law, the temperature needs to be in Kelvin. So this is the most restrictive in terms of what units everybody has to be in. The reason for that is R. R is a gas constant, 0.08206. The units of R are liters times atmosphere, Kelvin times mole. I personally use 0.08206 because that's the number they beat in my head, and I can't get it out as hard as I try. But nowadays, I will say that a lot of books and stuff will round this number to 0.0821. So that's okay as well. So if you want to use 0.0821, that's okay. And a lot of books will kind of round it these days. I personally, a lot of times, will use this number because, again, that is what's in my head. That is a constant value that you obviously need to know, right? Along with obviously all the other formulas here. That is also a value that is usually never given to you in a problem. They just assume that you know you have that available to you. So if you've come across a problem and you're like, okay, I got like a pressure, I'm looking for a volume, I got a temperature and some moles, kind of missing like R, that is a value, again, like I said, is usually not given to you in the problem. They just assume you know you have that available to you. So that's always a value that you just have like available to use if you need to. What is an ideal gas? We'll talk a little bit about it towards the end of the chapter, but essentially what makes something an ideal gas is really two things. One thing that makes something an ideal gas is when we think about the volume of an ideal gas versus the volume of the container it's in. The volume of an ideal gas under normal conditions is extremely small compared to the volume of the container they're flying around in. And that's why if you look at a lot of problems that you come across, when they mention the volume, they mention more of the volume of the container rather than the volume of the gas itself. And that's an ideal situation that the gas volume itself is super small. You don't have to worry about it. It's more about where it's flying around. And that's why when we think about gases, we think about it filling the container uniformly because it's just flying around the entire volume of the container it's in. The second thing that makes something an ideal gas is you could have multiple gases together in the same container. Under ideal conditions, they basically will not interact with each other. It would be almost like they are in that container by themselves, not with any other gas. So those are really the two main things that make something an ideal gas. I would say under normal conditions of pressures and temperatures, most gases will behave pretty ideally. And in this class here, all gases will behave ideally. When you go to 1A, gases will not behave ideally. They're known as non-ideal gases, or real gases they're sometimes referred to. And under real gases, that usually happens at really high pressures and very small volumes. And at very high pressures and very small volumes, you actually do have to take into account the volume of the gas itself, and you also have to take into account how it's interacting with other gas molecules. And what that ends up doing is turning the ideal gas law into a very scary looking equation known as the van der Waals equation with a lot of extra letters in it. But in here, everything will be an ideal gas. But when you do go to 1A, you will talk about real gases or non-ideal gases. Any questions on that there? Now, a couple of other important things here that kind of go along with this are a couple of terminology terms here that we see. One thing, we'll start with STP. STP stands for standard temperature and pressure. So in a problem, if they tell you, hey, this is at STP, they're actually giving you values. The temperature at STP is 273.15 Kelvin. The pressure is 1 atmosphere. So again, in a problem, if it says, hey, this is at STP or find the volume at STP, those are the pressure and temperature values you should use. If you want to know if it is at STP, they have to both be those things. So if it's not that 273 and it's not 1 atmosphere, then you're not at STP conditions. Now, one of the nice things about STP conditions is if you are actually at STP conditions, you could actually use this conversion factor, which is 1 mole of any gas will equal 22.414 liters. So that is a conversion that you could use at STP conditions only. So once again, if you are not at STP conditions, you should not use that conversion factor. Why would you want to use that conversion factor? You could use that conversion factor and avoid using the ideal gas law if you are under STP conditions. If you are not under STP conditions, you should definitely use the ideal gas law. By the way, if you're under STP conditions, you could still use the ideal gas law. You could use it with 273 for temperature and 1 atmosphere for the pressure. So the deal with the ideal gas law is this: you can be used under any conditions. It's kind of like a universal gas law. You could use it under any conditions, standard conditions, non-standard conditions. Just put the numbers basically in there. By the way, that is how we actually get the gas constant. If you take the ideal gas law, solve for R, and put in all your values at STP, 1 atmosphere for the pressure, 22 liters for the volume, 1 mole, and 273, that again is where our gas constant value actually comes from. Questions on that there? All right, so why don't you try one here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas at a volume of 5.43 liters and 69.5 degrees Celsius. Okay, so let's take a look. So once again here, just pulling in the information out. I'm looking for a pressure. I have obviously some moles here, 1.82. I have a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. So again, just looking at the information, obviously we only have one of everything. So that really does, as we talked about, eliminate all those previous sort of formulas. I could almost kind of see PV equals nRT. Reminder, as I mentioned, very much like this problem, R is, again, never usually given to you in the problem or even mentioned most of the time. So remember that is always a value that you have, and you do need to know it. 0.08206 or 21, if you want to use that version of it, it's okay. So we do want to then think about PV equals nRT. Obviously here we are going to solve for P. Once again, they're not really written as a fraction, but same sort of thing applies. We want to take the volume to the other side, so it will end up on the bottom, obviously by dividing it basically to the other side. That will give us P is equal to nRT divided by V. Unit-wise, our volume is good. It's in liters. Our moles are in moles. Our temperature, like normal, we do need to adjust to Kelvin, so we'll add our 273 to it. So 273, let's see, I punched that right, 273.15 plus 69.5, going to get us, looks like 342.65 Kelvin. Now we can put everything in, so our N, which is 1.82 moles, our R, which we always have, 0.08206. Again, this has all the units there, and if you're ever not sure what everybody else needs to be in terms of units, the R tells you what everybody has to be in. If you remember the units to go with R, that's what everybody else in this formula has to be in. So that everything cancels correctly. 342.65 Kelvin, all going to be divided by our volume here of 5.43 liters. The moles will cancel, the Kelvin will cancel, the liters will cancel. It is just going to leave atmospheres as the only unit left. So 1.82 times 0.08206 times 342.65 hit equals, divided by 5.43. That is going to give us a 9.42 atmospheres as our pressure in this particular case. Any questions on that one there? As I mentioned before, very common couple of kind of conversions that are oftentimes used here in this sort of formula. as I mentioned before, grams to moles using the molar mass. Also, the conversion for volume between liters and milliliters. That again is also a very common occurrence here in gas laws is taking. Okay, we're going to continue on here, I think. Any questions so far on what we're talking about? All right, so let's take a look then. If there's not another example here, maybe. There we go. Calculate the pressure in atmospheres exerted by 32.5 grams of SF6 gas in a steel vessel that has a volume of 252 milliliters and 45.5 degrees Celsius. I'm going to give you some numbers that might be helpful. Sulfur 3207 and fluorine 19. Okay, let's take a look here. So once again, we are looking for a pressure. We have 32.5 grams of SF6. We do have a volume that is 252 milliliters, and we do have a temperature that is 45.5 degrees Celsius. So again, we kind of have PVT. We have grams, but we can't get to moles from that, so that's N. So again, this is shaping up to be obviously a PV equals nRT situation here. We got a lot to do here in terms of units to get everybody in the right units. Um, Remember, not usually given to you in the problem, but we always have, again, our gas constant there available to use. So we do need to convert grams into moles. So we got 3207 for the sulfur plus, what was that, 6 times 19 there for the fluorines. And that's going to give us a molar mass here of, looks like 146.1 grams per mole. So we're going to use that to convert our grams into moles. So we'll go 32.5 grams of SF6 using the molar mass from the periodic table, 146.1 grams per mole. Again, we want the grams to cancel. And that's going to give us here 32.5. And we'll call it 0.2225 moles. Our volume also needs to be converted to liters. So here we would need to use our 1,000 milliliters as a liter. That's going to give us 0.252 liters. Lastly, like normal here, we need to add a 273.15 to that to convert that into Kelvin. 273.15 plus 45.5 looks like a 318.65 Kelvin. We should now have pretty much everybody in the correct units. And remember that the ideal gas law is the most restrictive in terms of units. So pressure in this case would be nRT divided by V, bringing it down to the other side. Putting in our values here, I'll go over here, I think. So our N was, where's my N there? There's 0.2225. My R 0.08206. RT here 318.65. All divided by our volume in this case, which is 0.252 liters. Again, because everybody's in the right units, they will agree and cancel out with our R value here. going to leave us atmospheres, which is the only unit left, which is a pressure, so that's good. So a 0.2225 times 0.08206 times 318.65 divided by 0.252, going to yield us a 23.1 atmospheres in this case, as again, that is the only unit that is left. So again, I would say in this problem here that you come across some very common conversions that you need to do using gas laws, grams to moles, milliliters to liters. Any questions on any of that there? Okay. All right, so that is the ideal gas law. And if we don't have enough gas laws, let's take a look at another one here. If you actually take the ideal gas law and you set it equal to R, and since R does equal the same number, you can set each of those things equal to each other for a 1 and 2 type situation. In most cases, the number of moles does stay the same. So that reduces us down to this gas law here, which is P1V1 over T1 equals P2V2 over T2. And here the temperature, no surprise, needs to be in Kelvin, obviously. Pressure can be any unit as long as they're the same. And same thing here with volume can be the other unit, any unit as long as they're the same. This is what is sometimes referred to as the combined gas law. Basically combines everybody together in this particular case. Now, if you were to invest your time to remember these formulas, which you do need to do at this school, which formulas would I remember to help me do that? This would be the one right here. So this would be the formula you would want to know. And from this particular formula, and be honest with you, if you actually remember this version of the formula, it's actually pretty good too. So if I take that version of the formula, which is P1 V1 over N1 and T1 equals P2 V2 N2 and T2, and if I remember this formula and I invest my time really into just remembering this formula, I come across a question and I need to pick out what gas law I should use. And when I read the question, it doesn't mention anything about moles, grams, moles, nothing's mentioned. It doesn't mention anything about temperature, or you're told it's held constant. All you have to do at that point is come to this formula and just scratch out what is not mentioned. And if I do that, that right there becomes Boyle's law that we learned earlier. If you take this formula and you come across a question where they do not mention anything about moles, or they tell you it's held constant, they don't mention anything about pressure. All you do is come over to this formula, scratch out the P in the end, scratch out the P in the end, and lo and behold, there is Charles' law that we learned earlier. If you take this formula and you come across a question where they don't mention anything about moles and they don't mention anything about volume, all you have to do is come to this equation, scratch out the V and N on both sides, and now you are looking at Gay-Lussac's law that we learned earlier. If you take this formula and you come across a question where they mention something like the pressure and the temperature is held constant, you come to this formula, you scratch out the pressure, scratch out the temperature, and there is our friend Avogadro's law. So if you learn the combined gas law, if you want to learn it like I just showed you there with the moles in it, it's not a bad idea, because pretty much if you know this gas law, you can pretty much get all the other gas laws that we learned earlier. All you have to do is scratch out what's not given to you, what's not mentioned, what's held constant, and what you are left with would most likely be the correct formula that you need to use. So that's a really good one. If I asked to invest my time knowing all these, I would go with my investment right there And just for good measure, know the ideal gas law by itself, and you'd be in good shape pretty much for any formula that you would need in terms of those gas laws. You know, so individually sort of remember all the other gas laws and stuff like that. Any questions on how that all works there? So essentially, just scratch out what's not given to you or held constant should leave you pretty much with either Boyle's law, Charles' law, Gay-Lussac's law, or Avogadro's law. And if you know that and Avogadro and the ideal gas law, you should be in pretty good shape. Any questions on that? All right, so let's try one here. Consider the sample of oxygen at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97 atmospheres. The pressure is changed to 8.25 and the temperature goes to 125 degrees Celsius. What is the new volume? So take some time, rearrange that equation. Okay, let's take a look. Once again here, just pulling out the information. We got a temperature of 27 degrees Celsius that goes with a volume of 9.55 liters and a pressure of 2.97 atmospheres. We are changing the pressure there to 8.25 atmospheres, and our temperature is going to 125, and we are looking for a volume. So you hopefully could almost see the combined gas law there as you kind of look at it. Once again, I'm going to call all the first ones ones and all the second ones twos. In terms of atmospheres and atmospheres, they're the same, so we're good to go. Like normal, we need to do our temperature conversion there. So we're going to add a 273 to our 27, 273.15. I'll go to the left here. It looks like 300.15 Kelvin. We'll obviously also add that to our 125. And now we really do have everything in the correct units. So we got P1, V1 equals R over T1 equals P2, V2, T2. Again, in this case, there's no mention of grams, moles, or anything like that, so I don't need the N in here. We are going to be solving for V2 in this case. So V2 is on top, so that's where we want to keep it. That does mean that our T2 over here needs to go up and our P2 over here needs to go down. Again, opposite location to do so. That will give us P1 V1 T2 divided by T1 P2. Once again, we are essentially multiplying and dividing when we're doing that. We're going to put everybody in the correct location. So that is P1 up on top, which is 2.97. That is V1 up on top, which is 9.55 liters. And our T2 up on top, which is 825 atmospheres. All divided by our T1, which is 300 there. 300.15 Kelvin. And our P2, which is 8.25 atmospheres. Again, atmospheres are going to cancel. And I feel like I put the wrong one there, didn't I? I did atmospheres twice on top there. That's not good. Let's try that again. That is our temperature. Or did I write it weird? Maybe I did. That should be our temperature up on top, which is T2, which is 398.15. Okay, that's better. All right, so I think we should be good there. We got our P1 of 2.97, our V1 of 9.55, our T2 398.15, our T1 on the bottom 300.15, and 8.25. So now we should be good. Again here, atmospheres and atmospheres will cancel Kelvin, and Kelvin will cancel. Our units are going to be liters when we're all said and done here. So on this one here, I'm going to go 2.97 times 9.55 times 398.15. I'm going to hit equals. I'm going to divide it by 300.15 hit equals, divide it by 8.25 hit equals, and you will end up with 4.56 liters as your answer in this case. Any questions on that one? Probably the one most people struggle with a little bit in the rearranging. So again, remember whatever you're solving for, it does need to be on top by itself, not on the bottom. Otherwise, it's 1 over that. So just be careful as you rearrange those things. Any questions on that there? Okay. That's what we just did. So the next thing we're going to talk about is stoichiometry that involves gases. And stoichiometry that involves gases is pretty much the same deal as regular stoichiometry. So in regular stoichiometry, as we talked about, and even limiting reagent stoichiometry, we have our 4 steps, which is we do want to make sure we have a balanced equation. We want to take whatever they give us and convert to moles. Remember at this point, if it is a limiting reagent problem, you may have to do a calculation. 3 is do your mole to mole relationship. And lastly, moles to some other unit. So what is the main difference here when we're doing gases? Somewhere along the way, in most cases, you're probably going to use the ideal gas law or some type of gas law is pretty much what you're going to use. A lot of times it is the ideal gas law. If you use it up front, you would be solving for moles. So it is possible to have to use the ideal gas law here to solve for moles up front instead of grams to moles using the ideal gas law to get your moles. You may not have to use the ideal gas law up front. You may just do grams to moles like normal. But a lot of times, I would say maybe more than up front, you will use the ideal gas law at the end of the calculation. So at the end of the calculation, you obviously will use the ideal gas law. I would say probably in a lot of cases, you'll be solving for volume is very common sort of question, like how much volume of this gas did you collect is a super common sort of question. So I would say that is the main difference between a regular stoichiometry problem and one involving gases. It's really the same steps, other than somewhere along the way, in most cases at the end, you are going to use some type of gas law to solve this problem. Any questions on that? I would say occasionally you will use maybe not the ideal gas law, but you could use something like the combined gas law that we just talked about as well at the end. You could also do what we talked about a little bit earlier. If you have a constant temperature pressure situation, you can avoid using the gas law and just kind of do the volume to volume relationship that we talked about. Again, remember that has to be a pressure, temperature, constant situation. So let's take a look at one here together and talk about how we get there. There's my arrow. So let's say we wanted to know the volume of CO2 that we produced at 37 degrees Celsius and 1 atmosphere when we started with 5.6 grams of glucose in this reaction. So if we take the information, we got 5.6 grams of glucose. We want to know how many grams of CO2. So this is really a basic stoichiometry problem. Some of the other important information we have in terms of our CO2 is the temperature is 37 degrees Celsius. The pressure is 1 atmosphere. Obviously here we are looking for grams of this guy. And we always have R, which is our gas constant. So again, that is always a value that's available to us. So if we think about the ideal gas law here for CO2, we have the pressure given to us. We have the temperature. We have R. We are looking for the grams in this case. Oh, no, we're looking for the volume. I'm sorry. We're looking for the volume. The volume. That would be much better. The volume. We are looking for the volume here. So the one thing that we are missing is the moles here of CO2. So that is where the stoichiometry comes into play. So we kind of check off everything else that we use. The only thing that we did not use is the grams of glucose. So we're going to start with our balanced equation, which we have. We're going to take what they gave us, which was this number here, and convert it to moles, right? So that's like your second step. To do that, we will need the molar mass of glucose. So that is 6 times 12.01 for our carbons, plus 12 times 1.008 for our hydrogens, plus 6 times 16 for our oxygens in this case. And that's going to give us a molar mass for glucose, 6 times 12.01 plus 12 times 1.008 plus 6 times 16 of 180.2, we'll call it, grams per mole. And again, that comes from the periodic table. So step number 2, we're going to take what they gave us, use the molar mass from the periodic table to convert that into moles. So 180.2 grams per mole. And we are now going to get our moles. And again, this is very similar to basically using the molar mass in grams. Obviously, exact same calculation here to get our moles like we normally do. Moles of C6H12O6. So step number 2, we're just going to convert to moles like normal. Remember that in this case, we are not interested in the moles of the C6H12O6. We're actually interested in the CO2. So that is the stoichiometry part. So step number 3, from the equation, we can see for every 1 mole of our glucose, we get 6 moles of CO2. So once again, in this case, it's just a basic stoichiometry problem here. So we're going to go 0.3108 moles of C6H12O6. We're going to do our mole-to-mole relationship. So we want to go opposites to cancel. So we're going to put this guy on the bottom. 6 moles of CO2 up on top. And the moles of the glucose will cancel. So we're basically going to take that 0.03 number and times it by 6, 0.1865 moles of CO2. That is really one of the last things that we're missing for CO2 to use the ideal gas law. We do need to convert our temperature here into Kelvin, so we'll convert that as well. So 273.15 plus 37, going to get us 310.15 Kelvin. We now have everything we need to go into our ideal gas law. Here we're going to be solving for, I'll erase some of that so I got something to write. We're going to be solving for our volume. So our volume will equal nRT divided by P. Again, dividing this to the other side to do so. And now we're ready to put in our values here. So I'll just kind of clean up a little bit here. So putting in our values for N, our volume will equal what we just calculated there, 0.1865. R is a constant, so we always have that value. Our temperature there, 310.15. All divided by our pressure, which was 1 atmosphere in this case. Atmospheres are going to cancel, Kelvin are going to cancel, moles are going to cancel, going to leave us liters as the only unit left, which is good. So we'll take our moles, we will times it by the ideal gas constant, and 310.15, going to get us 4.74 liters of CO2 would be produced in this case. By the way, that number would represent a theoretical yield in this case, right? Since CO2 is a product, that would be the theoretical yield of how much CO2 we should collect if we started with that 5.6 grams of glucose in this case. Question on that there. So again, it is the basic same four steps. It is not a limiting reagent problem in this case because we could not get moles of each reactant. So remember, that is sort of the reasoning of whether or not it's a limiting reagent or not. You absolutely could have a limiting reagent type problem in a gas stoichiometry as well, but just keep that in mind. Any questions on that there? All right, so why don't you try one then, maybe? So consider this reaction here. What volume of hydrogen gas at 27 degrees Celsius? Okay, so let's take a look. Again, I got a stoichiometry problem here. We're really given grams of phosphorus here, and we are eventually interested, though, in our hydrogen, which is a gas. So again, if we think about PV equals nRT here for hydrogen, we do know that the temperature is 27 degrees Celsius. We have a pressure is 1.25 atmospheres. Remember, we always have R available to us. And again, we are looking for the volume here. So we are looking for the volume. We have our pressure, we have our temperature, we have R. Once again, we are going to need to kind of use stoichiometry here to get to the moles so that we can solve for what we're looking for. At this point, we will balance the equation, which it is balanced. We will then need to convert our grams into moles. By the way, obviously, we're looking for a reactant here, so it's not a limiting reagent problem or anything like that. We only have basically grams of phosphorus. So we'll take our 5.65 grams of phosphorus, which is P4. We'll use the molar mass from the periodic table. So that is 4 times 3097 grams per mole of P4. Again, our grams are going to cancel. That's going to get us here 5.65 divided by, and by the way, that's 123, I think, 0.9 grams per mole, give or take. So that's going to get us here 0.04561 moles of P4. Remember, again, we're not interested in P4. We are interested here in H2. So that is really where the stoichiometry comes into play. So that'd be kind of like our third step here. That'd be like our second. This would be our first. So from the equation, we see for every 1 mole of P4, we actually got to put in there 6 moles of H2. So that is the conversion factor is going to allow us to get to H2. We will go 0.04561 moles of P4, a 1 mole of P4 to 6 moles of H2 in this case. So times that by 6, I believe. Going to get us 0.2737 moles of H2. Any questions on that so far? So at this point, we use our stoichiometry to now get really the missing piece that we needed to use the ideal gas law here for the H2, which is what we're interested in. Much like the last one, really the only thing we got to do here is convert our temperature into Kelvin. Everybody else is in the correct units. So a 27, 273.15, a 300.15 Kelvin. So again, here solving for V, nRT divided by P, putting in our numbers 0.2737 moles of hydrogen, 0.08206 liters atmosphere Kelvin mole, temperature 300.15 Kelvin, all divided by our pressure, which is 1.25 atmospheres. Atmospheres cancel, moles cancel, Kelvin cancel, leaves us liters left over. Gonna get us here, looks like about 5.39 liters of H2 in this case. This is not a yield because it's not a product. So this is just obviously how much of the other reactant that you would need, obviously, to put in there in this case. Again, hopefully you can kind of see it's really the same 4 steps. Again, as you can see, this is, I would say, super common kind of at the end to use the ideal gas law, but not always. You sometimes do have to use it at the beginning, but it's a very common sort of ending, I would say, looking for the volume. Any questions on any of those steps? Yeah.
6 moles of H2, 4 moles of P4 by mistake, but I ended up getting the same amount of moles for H2. So, like,
Uh, yeah, it shouldn't come out that way unless you didn't use the 4 on the molar mass. Yeah, that's why it compensated. So I wouldn't recommend it. Probably not a good idea. So, but that's probably why it worked out. You probably didn't use the 4 in that spot. Yep, yep, yep. Other questions on that? Okay. All right, let's take a look then at, not that one. Let's take a look at one more here, I think. This is similar to the experiment, actually, we're going to do, I think, on Thursday this week. So I want to give this one a go. Magnesium reacts with hydrochloric acid to produce hydrogen gas. What is the volume of hydrogen gas you would collect at STP by reacting 5 grams of magnesium with excess amount of HCl? So magnesium is 2431. It should be, I think, 2431. Don't think you need the others, but I'll put it up there just in case. And a reminder, STP means temperature is 273.15 and the pressure is 1 atmosphere, right? All right, so give it a go, see what you come up with. Okay, so let's take a look again at this one here. So obviously we got a stoichiometry problem happening. It already tells us the HCl is the excess reagent, so we already know it's not a limiting reagent problem. We do have our grams of magnesium, but ultimately we're interested in hydrogen. And STP does represent a temperature and pressure when you're given that. So again, 273.15 and 1 atmosphere. So if we think about our gas, which is our hydrogen, and the ideal gas law there, again, we have a pressure already, we have a temperature, we always have R, and in this case here, we are looking for a volume. So much like we've seen in the previous problems, we're missing N in this case. So we're going to use our magnesium to get to N, and we will convert that into moles. So we take our 5 grams of magnesium using the molar mass from the periodic table, 2431 grams per mole of magnesium. That is going to get us here 5 divided by 2431. We'll call it 0.2057 moles of magnesium. Again, we're not interested in magnesium. We want hydrogen, so that is the stoichiometry part that allows us to go from there to there. In this case, it's a straightforward one. 1 mole magnesium gives us 1 mole of hydrogen. So it is a 1-to-1 relationship, and that is what we could do here. 1 mole of hydrogen on top. We want to get rid of the magnesium, so it'll go on the bottom so that they cancel. Again, this is basically step number 2, step number 3 in our stoichiometry type of move. I could do that math there. We didn't change anything. Basically 0.2057 moles of hydrogen at this point. Now that we have the moles of hydrogen, once again, that was sort of the missing piece that we needed for our ideal gas law, much like we did previously there. We're going to solve for V by dividing the P to the other side. Putting in our numbers, 0.2057 moles of hydrogen. our gas constant, which we always have, our temperature 273.15 for good measure, all divided by our pressure of 1 atmosphere. Again, atmospheres will cancel, Kelvin will cancel, moles will cancel, going to leave us liters. So 0.2057 times 0.08206 times 273.15. That's going to get us 4.61 liters of H2. Once again, this would be a theoretical yield as H2 is a product in this case, and that would technically be how much you would have produced. First off, any question on those steps there? Could I have solved this another way? And the answer is you could have in this particular case. So let's talk a little bit about that as well. In this particular case, we were at STP, which means you could use that relationship we talked about earlier that at STP, 1 mole of a gas equals 22.414 liters, which means you could have picked up right around here. And instead of putting it into the ideal gas law, you could have just used that conversion because you were at STP. That 1 mole of H2 would equal 22.414 liters. The moles of H2 in this case would cancel, and you should end up with the exact same number that we got above, which is 4.61 liters of H2. So in this particular case, if you recognized it was at STP, you could have used this conversion, avoided really this last step here. If you didn't recognize it or didn't see it, it doesn't really matter. As you can see, you could go right into the ideal gas law and get the same answer. So once again, you can always go into the ideal gas law and you'll get the right answer. You don't even have to worry about that conversion if you don't want to worry about it. Any questions on stoichiometry involving gases? As I mentioned before, it is possible to have a limiting reagent type problem. You just have to do that limiting reagent step like normal. And you obviously would be able to get the moles of everybody to start with. That's how, again, you could recognize it. Any questions on that there? The next thing we're going to talk about in this chapter here is Dalton's law of partial pressure. And Dalton's law of partial pressure sounds quite complicated, but it really is not too hard of a concept. The idea here is pretty straightforward. If I have a container, for example, and in this particular container, the only gas molecules I have are gas molecules A, then the total pressure of this particular container is a result basically of the pressure from gas A, as that's the only gas molecule basically flying around in that particular case. Now, let's just say though I had a mixture of gases, which is very common how gases come. And let's just say I had A, B, and C gas molecules flying around there. 3 different gas molecules, types of gas molecules. When I look at the total pressure of this mixture of gases, it is a result of the partial pressure of A plus the partial pressure of B and the partial pressure of C. These are what are referred to as partial pressures because they contribute to the overall pressure when you add them together. Now, how do you get to the partial pressure? Well, I'll say probably in most cases, it's going to be a PV equals nRT situation is probably most cases. Now, if you remember, one of the things that we talked about a bit ago there was what makes something an ideal gas is you could have multiple gases in the same container, but they really will not interact with each other. So what that allows us to do in a situation like this is we could actually use the ideal gas law for each of those gases individually. So you could, if you had this situation, you could solve for P for the gas A. You could solve for P for gas B. And you could solve for the partial pressure of gas C by using the ideal gas law basically 3 times. So in this ideal situation, because they are not interacting with one another, you could almost think of them as being in there by themselves. The other nice thing, though, about this is because they are technically in the same container, and that container is probably in the same room, the temperature for everybody is the same, the volume for everybody is the same, and R is a constant, which means it is the same for everybody. So when you go to do the ideal gas law, for example, in this situation 3 times, really the only thing that will be different between all your gases is N, the number of moles, will be the only different thing in that calculation. So the temperature will be the same, volume will be the same. So if you basically just calculate the moles of each of those gases, you can then go with the ideal gas law 3 times. That will give you the partial pressures of each of them, add them together. That will give you the total pressure of the mixture of gases. Any questions on that? And again, because it is obviously the ideal gas law, everybody needs to be in the correct units for everything to work out correctly, just like we've been doing. So as I mentioned before here, we get a pressure and temperature added to each other, or two pressures together gives us our total pressure, and our volume and temperature is going to be the same for everybody. And again, if you have 2 gases, you would do the ideal gas law twice. If you had 3, you do it 3, and so forth. Now, this also means, for example, if you were given the total pressure, and maybe you were given the partial pressure of B, you could find the partial pressure of A by just subtracting the total pressure minus the partial pressure of B. So if you had just A and B in this mixture, and maybe they gave you that information, you would not have to use the ideal gas law. You could just actually subtract. So that's another sort of application, sometimes what you do in this total pressure situation. So why don't you give it a try and see what you come up with. If you have 5 grams of helium and 5 grams of neon in a 2.5 liter container at 27 degrees, we're looking for the partial pressures of each gas and also the total pressure here. So we're looking for 3 answers: partial pressure of helium, partial pressure of neon, and the total pressure. Helium is okay, so let's see how you're progressing. So obviously here we have one container. It's basically got helium and neon flying around in it. Now, because obviously they're in the same container, we do have a mixture of gases. Obviously, the volume for both of them are going to be 2.5 liters. The temperature for both of them will also be 27 degrees Celsius. And obviously, we have 5 grams of each. So in this situation, again, we can use the ideal gas law for each gas individually, as we assume sort of ideal conditions that they're not going to really interact with each other. We already got the volume and the temperature. Obviously, we're looking for the pressure. We always, once again, have R. So in this case, we do need the moles, and we are going to need the moles of each of the gases. So that's maybe a good place to start. We'll do moles of helium, and that's going to be our 5 grams of helium. Once again, we're going to use the molar mass from the periodic table to convert that into moles. 4.003 grams per mole of helium. That's going to get us here 5 divided by 4.003. 1.249, we'll call it, moles of helium. We're going to do basically the same thing for neon. So our moles of neon going to be our 5 grams. Molar mass from the periodic table, 2018 grams per mole of neon here. And that's going to get us for neon here, 5 divided by 2018, 0.2478 moles of neon. Remember, we just got to watch a couple things here, like temperature, 273.15. We're going to convert that into Kelvin so everything works out correctly. And that's again 300.15. So we really have now everything that we need to use the ideal gas law. And once again, we're just going to basically do two separate calculations, assuming they're kind of in there by themselves. So the pressure here of helium will equal nRT divided by V. Putting in our moles of helium, 1.249. Our gas constant, which again is a constant value, 0.08206. Our temperature in this case was, where did we go there? 300.15 Kelvin. All going to be divided by our volume, which is 2.5 liters in this case. Moles will cancel, Kelvin will cancel, liters will cancel. Going to leave us pressure, which is good because that is what we're looking for. And we will end up with, in this case here, looks like 12.3 atmospheres. That 12.3 atmospheres represents the partial pressure of helium in this case. First off, any questions on that calculation? Yeah. What unit is R?
Yeah.
R actually has 4 different units. It's all the units that you see in the ideal gas law. So if you look at R, R has these units. It's liters times atmosphere divided by Kelvin times mole. All 4 of those units go with R. And that's really why when we do the ideal gas law, this guy has to be in atmosphere, so it cancels. This one needs to be in liters, so it cancels. This needs to be obviously in moles, so it cancels. And this needs to be in Kelvin, so it cancels. So if you're ever not sure what the other units need to be, you could always look at the units there associated with R, and I'll tell you what everybody else has to be in to properly cancel. Yeah. Other questions? Okay. So now that we did helium, we're going to do neon. It's basically the same calculation. Really, the only difference is going to be the moles. Here, obviously, we want to use the moles of neon. And if we use the moles of neon in this case, it was 0.2478. Everything else is going to be identical because they're in the same container. And again, divided by 2.50 liters. Moles are going to cancel. Atmosphere is going to, Kelvin. Why did I keep writing atmosphere? So that's Kelvin. Kelvin are going to cancel. Liters are going to cancel. Going to be left with atmospheres there. Obviously, this is a Kelvin here. So we got 0.2478 times 0.08206 times 300.15 equals, divided by 2.5, a 2.44 atmospheres. That would be our partial pressure of neon in this case, right? How do I get the total pressure? What should I do with those two numbers? I should just add them together, yeah? I take the partial pressure of helium plus the partial pressure of neon. Those guys will give us the total pressure. So in this case, 12.3 atmospheres plus 2.44 atmospheres. It's going to give us a total pressure in this case of 14.7 atmospheres as our total pressure. Any questions on any part of that there? So I would say this is a super common way to get partial pressures. It really is just an ideal gas law, just done for each gas individually. And again, you get some numbers that are used for everybody, like the volume and the temperature. Any questions on any part of that there? All right. So I'm not going to worry about that for sure. So another situation that can occur that does create a partial pressure situation is very often, for example, in lab. We don't do this experiment anymore, but we used to do this experiment. So we do the other experiment with gases. But a lot of times when we collect our gases, for example, in lab, a lot of times we will use water and we will displace the water with the gas that's coming in. And that's basically what's happening here. This is a decomposition reaction of potassium potassium chlorate. And basically when you heat it, it will make potassium chloride and some oxygen gas. So as you start to heat this, this is going to decompose and make oxygen gas. That oxygen gas has nowhere to go but down here. And when it does so, it will then basically displace the water that's in this sort of jar. So you have this jar full of water to begin with. It will displace the water. You will end up with an empty space, and it's really not empty. It's actually where your gas ends up. So in this example here, in this sort of empty space, if you will, I'll quote it. You actually will have oxygen gas basically in there, and that's where it'll end up, basically in this sort of empty spot. But because of the way we collected the gas in this situation, the heat of a reaction here with water will also give us another gas that will actually come in, and that gas is water vapor. So we'll get some water vapor that will actually be collected with the gas we're actually interested in. Now, this is a very common way that we collect gases. In fact, you'll kind of do that on Thursday as well. When you collect your gas, you collect it with water. Now, the problem though is we're not really interested in the water's contribution. We're actually just interested in the oxygen. The water here is just like a byproduct of how we collected it. But it does create a partial pressure situation where the total pressure is the pressure of the gas you're interested in, like the oxygen here in this example, plus the vapor pressure of water. This is what is sometimes referred to as the vapor pressure of water. Now, what the deal with the vapor pressure of water is, typically you can go look that up in a table. And you can look it up in a table based off of the temperature that you ran the experiment out, and you can look up the vapor pressure of water. So usually when you do this type of collection, you have to sort of do this calculation to get rid of water's contribution. So basically the pressure of the gas I'm interested in would be the total pressure minus the vapor pressure of water. So it's almost like a correction value that you typically will do. Where do you get the total pressure? In the case of a lab, you get it from the barometer. You would go read the barometer for the day. That would give you the atmospheric pressure. In a book problem, they most likely will give you perhaps the total pressure or the atmospheric pressure. But in the laboratory in real life, you would go and actually take that reading yourself off the barometer. So this is a partial pressure situation that's very, very common in the lab, as that is a very common way that you're collected. How do you know you should do this type of calculation versus trying to do like an ideal gas law thing? There's usually some words that are written in the problems that tell you it is this type of situation. They usually will say something like you collected the gas over water. That's a key that you got to do this calculation. Or it may say that the gas was saturated with water vapor. That's like a key that like, hey, this is the situation that's happening. So those are the key words you kind of want to look at when you see a problem like that. Here is, like I said before, a table from your book, or you'll have a table in lab that you can look it up. But usually the vapor pressure of water, you look it up based on the temperature, and you would use that. You clearly would want to make sure that your vapor pressure of water you look up in the table is in the same units as the barometer reading or the atmospheric pressure. So you do want to make sure, you know, that one's on atmosphere and one's torr. Otherwise, when you subtract, you're not going to get the right answer. So you do have to make sure they are in the same units. So let's take a look at this one here together. A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr, and the vapor pressure of water is at 30 degrees is 31.824 torr. What is the partial pressure of the oxygen gas? Once again, there's my key terminology there that I'm looking for, or I see. It says it is saturated with water vapor. So that is the key, that basically you collected that gas with water. That tells you the total pressure is the pressure of the gas we're interested in, plus the vapor pressure of water. Once again, they were nice enough in this case to give us the vapor pressure of water If they did not give it to you, you would have to go to that table we just saw and look it up, obviously, the value. So we do have this one. We do have the total pressure. So that basically means 753 torr is equal to the pressure, in this case, of the oxygen, plus the vapor pressure of water that we got from a table. Our units here are the same, so we don't have to worry about anything not canceling correctly. So the partial pressure of oxygen is the total pressure minus the pressure of water vapor, which means 753 torr minus 31.824 torr. That is going to get us here 753 minus 31.824, approximately 721 torr. And that would represent the partial pressure of oxygen. Sometimes this is also referred to, a lot of times in labs, as the pressure of the dry gas. Yeah? The pressure of the dry gas. And it's the dry gas because we basically subtracted off water's contribution. So very commonly, that is sometimes how it is referred to. It also does want it in atmospheres. So remember that 1 atmosphere is 760 torr. That's our conversion factor, so 721 torr. Opposites cancel, so 760 torr and 1 atmosphere. The torrs will cancel, gets us here approximately 0.949 atmospheres, which would be our partial pressure here of oxygen, are the pressure of the dry oxygen gas, because we subtracted off basically water's contribution. Any questions on that one there? So again, that's a very common sort of partial pressure situation, either ideal gas law or something like this, where basically it's just kind of like a correction value in real life. You're just subtracting off that water's contribution that you're not really interested in. Any questions on partial pressures here? So to finish up this chapter here, again, this is the kinetic molecular theory of gases. A lot of these things that are in this you do need to know, but we did talk about it as we kind of went through the different parts of this chapter. Gases consist of tiny particles that are atoms or molecules. These particles are so small compared to the distances between them that the volume of the individual gas molecules are assumed to be negligible. Remember that this right here, by the way, number 2, is what makes something an ideal gas. So number 2 there on the list is one of the things that makes something an ideal gas, is we really don't consider the volume of the gas itself, like I talked about earlier. It's more about the container in an ideal situation. The particles are in constant random motion, colliding with the walls of the container. These collisions with the wall is what exerts the pressure. So as we talked about, the more collisions, the higher the pressure. Less collisions, less pressure. Particles are assumed not to be attracted or repelled to one another. This is the second thing that makes something an ideal gas, is that. So what happens in a real gas situation where they are attracted to each other? If you just think about it logically, for example, if we have a gas molecule in an ideal situation, it is not attracted to that gas molecule, for example, behind it, or repelled by it. So it has this as a free path to hit the wall, basically, right? And it's going to cause a certain amount of pressure. But if we introduce the idea of there is perhaps either an attraction or a repulsion between those two molecules, which does not happen in an ideal situation, but in a real situation it does. Let's say it's attracted. So what happens though is this guy is attracted to this guy. It's going to actually slow him down, right? And he's not going to hit the wall as fast or as frequently because there's going to be that kind of pull. Or he may even hit it a little faster in some cases if it's repelled by it. And that's going to affect the pressure. And in an ideal situation, we don't worry about that. In a real situation, we do. Lastly, the average kinetic energy of a gas molecule is directly related to its temperature. If you basically increase the temperature, you're adding more energy. If you lower the temperature, everybody's going to be moving around a lot slower. Now, a couple of things that we talked about in terms of our relationships. At high temperature, gas molecules are moving faster and hitting the walls of the container. And at lower temperatures, they're moving slower and less collisions. In terms of pressure and temperature in a rigid container, which is what happens in Gay-Lussac's law, if you increase the temperature, you will see an increase in the pressure, as we talked about. And if you decrease the temperature, you'll see a decrease in the pressure. Last one here is Charles' law that we talked about. If the temperature increases, the way it's able, again, to keep the pressure constant is to increase the volume. If you lower the temperature, the way it's able to keep that pressure constant is it will lower that volume. Any questions on that there? One last thing that sort of relates to that I wanted to mention that I forgot there as we looked at this example here. Where was that example? Right about here, hopefully. Nope. This guy right here. So when we look at, for example, these sort of partial pressures, one of the things that makes something an ideal gas, as we said, is that they basically don't attract each other. And that's why we could do a calculation like this, right? It is because we could assume that they're in there by themselves. There's no interaction between the different gas molecules. In addition, when we look at this between, say, helium and neon, right? The one that's contributing most to the pressure is which gas in this case? Which one is contributing the most pressure? It is helium, right, at 12 versus neon that's at 2. The reason helium is actually causing more pressure has to do with the molar mass of helium. Helium is 4 grams per mole. Neon is 20 grams per mole. So helium is a much lighter gas, and because it's lighter, when it's flying around, it's actually moving a lot faster than neon. It has a greater velocity, and because of that, it's having a lot more collisions than neon is having in the same container at the same temperature, and it has to do with the difference in the mass. So a lighter gas will fly around a lot faster, will have a faster velocity than a heavier gas at the same temperature. And again, that's why we see a very big difference in the pressure of helium versus neon in this case. Yeah.
Like this, there's 2 elements and one significantly lighter than the other. It'd be safe to assume that one is contributing more to the pressure.
It should, yeah, it definitely should. It's what you'll learn about it in probably 1A. It's what's referred to as root mean square velocity. And because of the mass of the gas, if it's lighter at the same temperature, it will definitely be flying around faster, which would definitely cause it to have more collisions. If you have basically the same gas at different temperatures, at the higher temperature, you should see more collisions because it's moving faster because of the energy. And at lower temperatures, you see less collisions and the pressure should be a little bit less in that case as well. Yeah. Other questions? All right, that wraps up chapter 13.